Hello everyone and welcome back. Today we are going to learn about the force of buoyancy. The force of buoyancy is an equal and opposite force to gravity as an object is submerged in liquid. Everybody has experienced a force of buoyancy. Imagine when you went to the beach, you took a beach ball and you tried to hold it underwater. What would happen? You would experience a net upward force, and that upward force that you would experience, that is the force of buoyancy. The force of buoyancy is very important because it keeps entire ships afloat. Think about it. An aircraft carrier weighs approximately 1 million tons, and that is seamlessly able to float on the surface of water, and that is because of the force of buoyancy. But on the same token, imagine taking a piece, just a regular piece of steel, and placing it on the surface of water. What's going to happen? The piece of steel will easily sink to the bottom. So, the force of buoyancy. The first person to actually study the force of buoyancy was Archimedes. And we have what is called the Archimedes principle. And it states that any fluid applies a buoyant force to an object that is partially or completely immersed in it. The magnitude of the buoyant force equals the weight of the fluid that the object displaces. And that is very important because it gives us a formula to calculate the force of buoyancy. Before we explore the formula to calculate this, let's see where this force of buoyancy comes from. So we're going to go right here to our trusty Jamboard, and we are going to imagine the following scenario. Imagine we have a ship and it is submerged. I can't draw well, but imagine here this is the ship and we place it in water. So what's going to happen? When you place the ship in water, it is going to displace some of the liquid. It's going to push it out of the way. In turn, the liquid, it is going to apply an equal and opposite force onto the ship, and it's going to be at every part that is submerged. And that is what basically creates the force of buoyancy, and it opposes the force of gravity. In other words, the force of buoyancy is a reactionary force, and it comes from Newton's third law. For every action, there's an equal and opposite reaction. So going back to the way we calculate now the force of buoyancy. Everybody knows how to calculate the force of gravity. We've seen this very, very well in AP Physics 1 and in Regents Physics. So now let's see how to calculate the force of buoyancy. The force of buoyancy, we said, is the weight of the water that is simply displaced. So what is really the weight? The weight, of course, is the mass of the water times g, acceleration, and the mass now, we would have to use the density formula and see that that is going to be, that's the force of buoyancy, that is going to be rho, which is density, times volume, times g. So the force of buoyancy now becomes rho vg. And that, ladies and gentlemen, is the force of buoyancy. So let's go and check one of our first problems and solve it. So, clear this frame. So going back to our presentation, let's check this out. So as you can see over here, we have an object and we place it on the surface. If it floats, that means that simply the force of gravity at that point is going to equal the force of buoyancy. Now if you place some more weight on that object, it's going to be submerged further, and that's going to increase the force of buoyancy. And at that point, the force of gravity is going to equal the force of buoyancy. So let's look at our first problem. Imagine we have a raft that is made up of solid, square pine wood. We have to determine whether the raft floats in water, and if so, by how much it's beneath the surface. So let's go and answer the first problem, okay? We have to find out if it is going to float on the surface. So what do we say? That is basically an interplay between the force of gravity and the force of buoyancy. So we would actually have to figure out the force of gravity and in relation to the force of buoyancy. So what are the dimensions? That's all really we need. The dimensions are 4 meters length, 4 meters width, and of course, 0.3 meters in height. So let's go back to our Jamboard, okay? And I'm going to draw it right over here. This is our raft. And what do we basically say? It is 4 meters length, 4 meters width, and the height of it, the thickness really of it, is going to be 0.30 meters, okay? Anybody see that? So what do we say? When this is placed in water, what's going to happen? We're going to have the force of gravity, and when it's submerged in water, this is F of G, and we are going to have the force of buoyancy, okay? As you can see right there. So first, in order to see if it's going to float, we got to see if the force of buoyancy is going to be greater than the force of gravity. If not, then it's going to sink. So let's see. Let's first calculate the force of gravity of this pine wood raft. So here's the force of gravity. So how do we calculate the force of gravity? It is going to be m times g. And again, m, we're going to use the density formula, okay, and we are going to see that it's going to be, again, rho v g. So what is the density of pine wood? That is going to be 550. You can look that up. That's going to be in kilograms per meter cubed times the volume. So what's the volume here? Length, width, and height. So we have 4 times 4 times 0.30. So we have 4 times 4 times 0.30. Okay? And of course, we have now G, and that's going to be, of course, 9.8. So if we take all these and we multiply together, we see now that the force of gravity is going to be 26,000 newtons, just like that. So now what do we have to do? Now we got to find the force of buoyancy and compare these two. So let's find out the force of buoyancy. So if you remember correctly, the force of buoyancy really is the water, the weight of the displaced water. Sorry, it's not really working that well. But here's the force of buoyancy, okay? It's going to be m again times g of water. So that's the force of buoyancy. It's going to be equal to rho vg. We all know what the density of water is. Density of water, of course, is going to be 1 times 10 to the third times, now the volume, which was what? 4 meters times 4 meters times 0.3. And of course, G, which is 9.8. So, the force of buoyancy, if we multiply all three, we see that it's going to be 47,000 newtons. So what does this mean? When we compare it with the force of gravity, it's only 26,000. We see that because the force of buoyancy is a lot greater, that means that the object is going to float. Okay, so now, the second part of the problem simply asked us, okay, how much of it is going to be submerged? So remember what we said. When we take an object, we place it in water, what's going to happen? The force of buoyancy at that point is going to be equal to the force of gravity. Okay? Those two forces must be equal and cancel each other out. That, of course, if you recall correctly, that's Newton's first law. An object at rest will remain at rest unless acted upon by an outside force. So once again, the force of gravity, F of G, is now going to be equal to the force of buoyancy. It's not going to be the total buoyancy as we just calculated, because why? That is the buoyancy for the entire object. But rather, it is going to be submerged only up to the point where the force of buoyancy now equals the force of gravity. So the force of gravity, we already calculated it to be 26,000 newtons. So now we got to calculate the force of buoyancy that corresponds to this. Okay, so what is the force of buoyancy? Again, it is going to be rho v g. So here we have 26,000. Rho, of course, is density of water. Everybody knows what that is. That is 1 times 10 to the third. And now we see the volume is length, width, and height. So we have the length, we have the width, and now we're trying to find the height. So this is now our x. This is what we're trying to solve for. And of course now times g, which is the acceleration due to gravity, which is 9.8. So if we go ahead, okay, and we divide both of these unknowns and versus unknown, we're going to see that the height, this which is what we're trying to solve for, it is going to be 26,000 newtons. We divide it by the density of water, 1 times 10 to the third. We bring it on this side of the equation, times 4 times 4, and of course times 9.8. We're going to see that when we do this calculation, it is going to be approximately 0.17 meters. In other words, so even though it is going to be the entire thickness of the pine wood is 0.30, only 0.17 is going to be submerged, and 0.13 meters is going to be left exposed in the air. And that's how much is going to be submerged. And if we go back to our presentation and we double check, we will clearly see that here it is, our raft. Okay, here of course is the force of buoyancy. That's the maximum force of buoyancy. We said 47,000 newtons. That's exactly what we calculated. And with 26,000, of course, that's the force of gravity. So we know that the raft floats. And then finally, if we make the force of gravity equal to the force of buoyancy, and we solve for h, we see that it's going to be 0.17 meters, and only 0.17 meters is going to be submerged, and as we just said, 0.13 meters is going to be outside of the water. Thank you very much. I'll see you in class.